Imagine a square with 4 sides, flat on a page. Now extend lines from each corner, pushing straight up into the third dimension to form a cube. Next, take all 8 corners of that cube and draw new lines from them, this time piercing into a 4th dimension, perpendicular to every existing line in the cube. This shape is called a hypercube, or a tesseract. Visualizing objects in higher dimensions is incredibly difficult. But in the mid-19th century, some scientists in England believed that anyone who could do so would be greatly rewarded. For many Victorians, the 4th dimension represented a spiritual realm, a source of divine connection. It began with mathematicians like Bernhard Riemann, who developed new kinds of geometry beyond the familiar triangles and parallel lines. From there, the imaginative Victorians turned the 4th dimension into an almost magical domain, a place for communion and wonder. P. Lovecraft, an author born in New England toward the century's end, the higher dimensions held only horror. In his story, The Dreams in the Witch House, a student named Walter Gilman rents a room with bizarre angles. He is haunted by nightly dreams, pulling him into higher dimensional planes filled with gods and monsters. This Lovecraftian fear is primal and inescapable, a fear of the unknown, of the true scale of the universe, and of what lies beyond. Yet some are brave or perhaps foolish. Certain scientists have peered into the cosmic depths, searching for clues in those hidden dimensions. A century after Lovecraft wrote of their terrors, we now suspect there might be some truth to these ideas, though not exactly as he imagined. It turns out we may need to consider extra dimensions to understand the cosmos, but from a perspective lower than we thought. Our entire universe might be nothing more than a thin, two-dimensional membrane. Encountering science so young clearly shaped his future. His story reminds us how powerful early curiosity can be. Nurturing that spark is a goal for many educational efforts. Monthly hands-on projects are available for all ages, from toddlers discovering the world to teens and adults tackling advanced science, engineering, and art. Many families enjoy these monthly deliveries, building projects like planetariums, mixing constellations, and exploring orbital mechanics. The excitement of opening a new box and the reusable nature of the projects keep the engagement high, with families eagerly awaiting each delivery. To inspire young scientists and engineers, special offers can make these experiences more accessible. Perhaps Gilman studied too hard. Non-Euclidean calculus and quantum physics are enough to strain any mind. Mixing them with folklore and searching for a multi-dimensional reality would surely create mental tension. Like Gilman's exploration of his rented room, the journey to understand higher and lower dimensions is strange. It starts in an unlikely place, not with quantum studies or cosmology, but with an attempt to build more efficient steam engines. On October 15, 1815, Napoleon, once Emperor of France and master of half of Europe, stepped onto his new domain, the tiny island of St. Helena. This was his second exile and final prison, from which he would never return. In his final years, he insisted his attendants wear military uniforms and evening gowns, struggling to accept his defeat at Waterloo. That defeat was final. His glory days were over. He left behind a fragile restored monarchy in France, a regime hostile to anyone associated with the exiled emperor, including a young engineering officer named Sadi Carnot. Born in 1796, Sadi was the son of Lazare Carnot, a brilliant mathematician and commander in the French Revolutionary Army who navigated Napoleon's rise. Sadi was less fortunate. He kept his military position, but was often passed over for promotion due to his family's ties. Eventually, he took a pay cut for a nominal role, allowing him time for intellectual pursuits that would change our understanding of reality. Believing French engine inefficiency contributed to their defeat, he sought to mathematically describe the perfect engine. In an essay titled Reflections on the Motive Power of Fire, published in 1824, his work went unrecognized in his lifetime. But Carnot had unknowingly laid the groundwork for a new kind of physics. Decades later, his book caught the attention of Rudolf Clausius, a German physicist. Something in Carnot's work ignited his imagination. In 1850, Clausius formulated what became the second law of thermodynamics, and 15 years later, he introduced the concept of entropy. He had no idea what he unleashed upon the world. Thermodynamics rests on three basic laws. The first is a version of energy conservation. Energy cannot be created or destroyed, only transformed. The second law, first stated by Clausius, says entropy never decreases, meaning heat doesn't spontaneously move from cold to hot objects. The third law states that a system's entropy approaches a constant as it nears absolute zero, implying that temperature can never actually reach that point. Central to the second and third laws was this new concept of entropy. Scientists from Newton's time thought heat was a particle moving between objects. Clausius disagreed. While energy is conserved, not all energy is usable. For example, in a motor, some energy creates movement, while some is lost to friction. In cooking, some energy is lost as light and excess heat. Clausius reasoned that heat could be transformed, and we needed to track useful versus useless heat. He called this non-usable form entropy. The three laws worked. They explained experiments and made predictions, but they seemed created from nothing. Where did they come from? What did they mean? After pioneers like Carnot and Clausius passed, a new generation sought to understand the mathematical world they created. These explorers would find deeper connections to reality's true nature than ever expected. It must be splendid to command millions in great ventures, to lead 100,000 to victory. The exploration of thermodynamics would profoundly impact Ludwig Boltzmann, an Austrian physicist born in 1844, over a decade after Carnot's death, and more than 20 years after Napoleon's passing on scent. Helena Boltzmann, a modern scientist, sensed something deeper in the three laws, linked to the microscopic nature of materials. At the time, scientists were beginning to classify elements like hydrogen and oxygen and understand their properties. Most suspected these elements were made of fundamental units called atoms, but proof was elusive. Boltzmann's genius was to unite the budding atomic theory with thermodynamics. He envisioned gases and fluids as countless tiny particles, studying their interactions to explain large-scale thermodynamic properties. He was proven right. His revelations began with entropy. In 1877, Boltzmann created a new definition of entropy based on the behavior of microscopic particles within a whole, not a single mass. His definition counted the number of possible arrangements of tiny particles leading to the same observable property. To understand this, imagine cleaning your kitchen. You put dishes away, take out trash, and scrub grout. After hours, the kitchen is spotless, everything in its place. Boltzmann would call this a low entropy state. The property is cleanliness, and only one arrangement of everything achieves it. In his terms, only one microstate leads to the macrostate of cleanliness. A day later, after living life, the kitchen is less clean. It's now in a higher entropy state, slightly dirty. Many microstates can produce this observable property. A glass in the sink, a crumb on the counter, a ring on the table. Many more ways exist to be untidy than tidy. This connects entropy to disorder. Strictly, entropy measures the number of microstates leading to a specific thermodynamic state like pressure or temperature. But higher entropy means more available microstates and more disorder. This link between microscopic particle arrangements and a key thermodynamic concept birthed a new branch of physics, statistical mechanics. We now understand thermodynamics arises from statistical mechanics, especially after Einstein proved atoms exist in 1905. For example, temperature in a gas is the average kinetic energy of its particles. Hotter temperatures mean greater kinetic energy, so air particles move faster. When we put our hands in hot gas, particles slam into our skin, transferring heat. The key to statistical mechanics is that we don't need to know every particle's properties. We don't track each air molecule's position and momentum. Instead, we use probabilities, like counting microstates or computing averages. But these 19th century explorers weren't opening doors to new dimensions. They were building a mathematical toolkit. Any object with heat could be described by entropy, and entropy could be described by microscopic motions. In coming decades, these tools would be applied to the most unexpected places, objects that seemingly shouldn't have heat, like black holes. Exploring black hole thermodynamics would reveal the first hints that something was very wrong with the universe. The dreams were wholly beyond sanity. As Lovecraft's story continues, Walter Gilman's dreams take him to a bizarre other world, a place he believes is higher dimensional, full of abysses with inexplicable material and gravitational properties. Lovecraft writes, "The abysses were crowded with indescribably angled masses of alien-hued substance." Luckily, in our journey to the universe's most extreme place, the logical endpoint of thermodynamics, we have a guide experienced with impossible demons. Jacob Bekenstein was devoutly religious, yet this didn't hinder his exploration of the universe's extremes, a balance many physicists have struck. Newton was a devout Christian, and Georges Lemaitre, father of the Big Bang, was a Catholic priest. Bekenstein delighted in unfolding God's mysteries, seeing the study of nature as worship. The more we learn, he believed, the closer we come to knowing God. Yet, his most famous work in the early 1970s brought him to the brink of something more demonic than holy. Black holes, arguably the universe's most powerful destructive force. Nothing survives a black hole encounter, not planets, stars, or sometimes even galaxies. At first glance, they seem unrelated to thermodynamics, statistical mechanics, or hidden dimensions. Emerging from Einstein's general relativity, they are, in Nobel laureate Subramanian Chandrasekhar's words, the most perfect microscopic objects in the universe, constructed solely from space and time concepts. But this perfection created headaches, especially regarding two mysteries tied to their nature. First, the singularity, a point of infinite density at their center, as predicted by relativity. Infinite densities can't exist, so this indicates relativity is incomplete, needing a more fundamental theory. Unfortunately, singularities are inaccessible, locked behind the one-way event horizon. You can cross it, but like a Lovecraft adventurer, you can never share your findings. Event horizons present the second mystery. Black holes are the only places where you can enter but not leave. Are they truly points of no return, or is there more? These questions drove Bekenstein. Singularities were unsolved, but event horizons were equally mysterious and observable. By 1973, Bekenstein discovered something uniquely strange about black holes. Despite their fearsome reputation, they are absurdly simple from the outside, with only 3 quantifiable properties: mass, electric charge, and spin. No matter what falls in stars, gas, planets, or people, all information is hidden behind the event horizon. We only see those 3 properties. If 2 black holes from different sources have the same mass, charge, and spin, they are indistinguishable. Bekenstein called this the no-hair theorem, meaning black holes are bald of information. His mentor John Wheeler loved the phrase. Physicist Richard Feynman found it obscene, but it stuck. Some theorists thought black holes had 0 entropy, but Bekenstein realized the opposite. They must have entropy, or else tossing material in would destroy information, violating quantum mechanics. But how much entropy? He proposed black hole entropy is proportional to their surface area, the event horizon's size. Larger black holes have more surface area and more entropy. This led Bekenstein to make perhaps the most bizarre statement about black holes. He proposed the second law of black hole thermodynamics, that event horizons never shrink. This mirrored the second law of thermodynamics, where entropy never decreases in a closed system. Since he linked entropy to surface area, this new law followed. At the time, it was a conjecture, a bold guess. Then came Stephen Hawking. Unlike Bekenstein, Hawking wasn't religious. He said, "God is the name people give to the reason we are here." There's no record of tension between them. Hawking's issue was with the physics. He argued black holes couldn't have entropy because they didn't radiate heat, so thermodynamic terms didn't apply. Hawking set out to prove Bekenstein wrong, but found he was right. By studying event horizon evolution, Hawking discovered that through a quantum quirk, particles could escape. Black holes weren't black. They emitted a tiny amount of radiation. Hawking's 1974 result was a bombshell. Black holes emitted radiation, later called Hawking radiation, with smaller holes emitting more. This wasn't all. Hawking radiation and Bekenstein's entropy insights created perhaps modern science's greatest paradox, the black hole information paradox. Bekenstein's second law was ruled out. Black hole surface areas don't always grow. They shrink as Hawking radiation saps mass. But Bekenstein was correct that black holes have entropy. If they didn't radiate, information would just be hidden forever. But black holes eventually disappear entirely, taking their information with them. Hawking found the radiation was random, carrying no information. If information didn't escape via radiation, where did it go? This paradox suggested black holes could destroy information, contradicting quantum mechanics. Information can never be destroyed. So either Hawking was wrong about the radiation's nature, or Bekenstein was wrong about black holes being bald. This paradox has tantalized physicists since the 1970s, offering clues about dimensional reality. Our story began with Carnot and efficient steam engines. Clausius refined this into thermodynamics and entropy. Boltzmann later showed thermodynamics arises from more fundamental physics. Now, black holes show thermodynamic-like properties with radiation and entropy. If thermodynamics comes from deeper physics, perhaps black holes do too. But what does this reveal about reality? The key may lie not in their hearts, but on their surfaces. Parallel to Bekenstein and Hawking's work, another line of research emerged, not on black holes or astrophysics, but on light and lasers. There, scientists found that in special cases, our three-dimensional universe wasn't always necessary. Sometimes two dimensions sufficed. Walter Gilman's dreams overtake him, bringing him to otherworldly dimensions, and he loses his grip on reality. Just as Gilman crosses into higher dimensions with dire consequences, can we glimpse these extra dimensions through theoretical physics? And what would it mean for our universe? To explore this, we go back to the early 20th century and a young boy on the front lines. Born in 1900 in Budapest, Dennis Gaber served in the Austro-Hungarian Army's Artillery Corps against Italy in World War I. Between wars, he studied in Germany, excelling in electronics. In the early 1930s, the Nazi regime threatened him due to his Jewish heritage, so he fled to Britain in 1933. There, he pursued his fascination with electrons, light, and lasers, making a remarkable discovery: holography. When you take a photo, most information is lost. You can walk around a mountain vista in 3D, but a photo locks one perspective forever. Gaber found a way to encode 3D information onto 2D film by interfering light from multiple sources, recording how light bounces off an object. When light is shown the same way, the hologram recreates the original light pattern, allowing you to walk around the projection as if it were real. Invented in 1947, holography didn't go mainstream until Gaber won the Nobel Prize in 1971. The public saw it as sci-fi novelty, like Princess Leia's message in Star Wars, or through cheap imitations like holographic stickers. But physicists saw deeper implications. In special cases, a 3D world could be reduced to 2D without losing information. Central to this revolution was another man caught in World War I's chaos. I could smell the war coming. Claude Shannon started at Bell Labs in 1941, contributing immensely. He thought constantly about math, writing equations on napkins. A colleague called him intellectually insufferable due to his brilliance and impatience. During the war, he worked on cryptography, meeting Alan Turing. After the war, in 1948, he wrote a groundbreaking paper on communication and cryptography, devising a way to measure the information needed to describe an unknown thing's states. Surprisingly, his formula resembled Boltzmann's entropy formula, so he used the same term, making entropy nearly synonymous with information. Shannon's work was a landmark in information theory and computer science, quickly gaining traction in physics. What matters to physicists is a system state, a list of all properties like particle positions and momenta to predict future behavior. Sometimes this list is simple, like tracking a projectile's trajectory. Other times, it's immensely complex, like for gases, where tracking every molecule is impossible, so we use summaries like temperature and pressure. Information is at the heart of physics' predictive power. Knowing all information and the laws of physics lets you predict the future. Quantum mechanics altered this with fundamental uncertainty, introducing probabilities, but the principle remained. Track information, predict outcomes. Shannon's choice of entropy was no accident. There's a clear mathematical link between a system's entropy and the information needed to describe it. Boltzmann's and Shannon's formulas from different fields were eerily similar. This connection led John Wheeler, Bekenstein's mentor, to propose it from bit. That information, not matter or energy, might be reality's core. Even without going that far, the similarity means that any natural process following thermodynamics gives us a measure of its information content. As Bekenstein found and Hawking confirmed, black holes behave as thermodynamic systems. Bekenstein's investigation into information falling into black holes led him to argue they have entropy. Later, he discovered black holes have more entropy than anywhere else in the universe. From Shannon's work, this meant black hole surfaces contain the most information possible. To quantify this, Bekenstein used Planck units, created by Max Planck, the father of quantum physics. These units describe the scale where quantum mechanics dominates, combining constants like the speed of light and gravitational constant. 6x10 minus 35 meters is the smallest possible distance, where space-time breaks into quantum foam. In 1981, Bekenstein used Planck lengths to explore how much quantum information a volume contains. He found a maximum entropy limit, and black holes hit that maximum. Their entropy and information is proportional to their surface area. Adding one bit of information increases their surface area by exactly one Planck area, Planck length squared. Black holes contain the maximum possible entropy in a given volume, and when information is added, their surfaces grow proportionally, not their volumes. This wasn't just true for black holes. These findings led to a bold proposition. Perhaps black holes are holograms. Maybe they exist in fewer dimensions, just surfaces with no interior. If so, nothing truly falls in. Material stays on the event horizon because that's all there is. Hawking radiation would emit from this surface. In this view, both Bekenstein and Hawking were slightly wrong. Black holes need hair, information on their surfaces, and Hawking radiation must carry information in a subtle, entangled way. So black holes might be emergent phenomena, operating at a quantum level but appearing as simple 3D objects. But this wasn't the end. Black holes are pure gravity, geometric punctures in space-time. What they teach applies to the entire cosmos. What would we find by exploring further? Only by moving forward would we know. It would be barbarous to suggest what killed Gilman. There was virtually a tunnel through his body. Walter Gilman's quest kills him after encountering strange creatures in extra dimensions. He knew the dangers but couldn't resist. His dreams took him beyond our universe, to realms his mind couldn't comprehend. Following physics to the edge of understanding quickly becomes overwhelming. Perhaps that's why Juan Maldacena prefers sparse offices. A simple desk, chair, chalkboard, maybe a window. No distractions, just privacy to let his mind wander. For me, any quiet place works. Born in Argentina, Maldacena was a prodigy, reaching Harvard and then Princeton's Institute for Advanced Study by age 33. This institute, free from students, has hosted giants like Einstein, Oppenheimer, Ed Witten, and Andrew Gu. It's a center for cutting-edge theoretical physics. Maldacena was chosen for good reason. In 1997, his first major insight rocked physics and math, cited over 20,000 times, making it one of the most cited physics papers ever. He discovered a doorway to a new realm, suggesting not just black holes, but the entire universe might be a dim projection of a two-dimensional reality. This paper didn't appear in a vacuum. Between Bekenstein's revelations and Maldacena's insight, others had explored holographic ideas. In the early 1990s, Dutch theorist Gerard T. Hooft, a future Nobel laureate, proposed the universe might be a hologram. The thinking was that black holes teach us about gravity's fundamental nature. Einstein showed gravity is the warping of space-time by matter and energy. Understanding gravity through a quantum lens could change our picture of space and time, which are more fundamental than the matter within them. Black holes teach us about gravity, which teaches us about space-time, which teaches us about the universe's construction. So, what were black holes teaching? They showed gravity cares more about surfaces than volumes regarding information. But this wasn't a physical theory. Enter Maldacena. The most popular proposal for a quantum theory of gravity is string theory. It suggests matter isn't made of point particles but tiny strings, each around Planck length size. Different vibrations produce different particles, including the graviton, gravity's quantum force carrier. String theory has two major issues. It requires extra dimensions. Early versions needed 26, modern ones 10 or 11, and nobody has turned it into a working theory. After half a century, we don't know how extra dimensions curl up, how their shapes affect string vibrations, or how this connects to space-time. In 1997, Maldacena found a clue in black holes' holographic nature. Inspired by the link between black hole information and surface area, he explored holographic concepts in string theory, discovering the ADS/CFT correspondence. ADS stands for anti de Sitter space, a toy model universe empty of matter but with a negative cosmological constant. CFT stands for conformal field theory, a special quantum field theory. Maldacena found that for an anti de Sitter universe in 5 dimensions, instead of solving string theory in its volume, projecting onto its 4-dimensional surface transformed equations into solvable conformal theories. In other words, maybe string theory is hard because we're not seeing the universe as it truly is. If the universe is a hologram, we should focus on its 2-dimensional surface, where equations become solvable. Nearly 20 years later, the ADS/CFT correspondence remains a cornerstone of holographic principles. But it's not proven, and while it works in Maldacena's toy universe, we don't know if it applies to our real cosmos. Despite this, physicists have embraced it. Most modern string theory work focuses on extending this correspondence. It's that seductive. It was the first convincing link between unknown and known physics, a bridge between string theory and quantum theory. So from Carnot to Clausius, Boltzmann, Shannon, Gaber, Bekenstein, and Maldacena, a chain of thought leads to an unlikely conclusion. Our universe may be a hologram. We stand on knowledge's precipice. Behind us are centuries of exploration. We don't know if the universe is a hologram or if information is reality's fundamental unit. We don't know the connections between gravity and thermodynamics. But if these ideas are real, it profoundly changes our cosmic view. Unfortunately for Victorians, these insights don't reveal a spiritual fourth dimension. Instead, they reduce the universe to two dimensions, suggesting our 3D experience is an illusion. Real information and physics reside on the boundary, where everything, you, me, stars, and galaxies, would exist. Like Lovecraft's creatures, we wouldn't perceive the full complexity of quantum information in this hidden 2D membrane. It's too removed from our conscious experience, constrained by our biological brains. Many disagree. Despite holographic theory's allure, nothing has been proven after decades. We haven't cracked string theory or proven ADS/CFT. Black holes remain mysterious. String theory is on shaky ground after the Large Hadron Collider found no evidence for supersymmetry, a key component. Without string theory, the holographic program may be at risk. Perhaps steam engines are just steam engines, and black holes only coincidentally resemble them. Maybe we misunderstand entropy and quantum information. Perhaps we've been wrong all along. Is this a warning? Is the universe telling us something? What will we find if we keep exploring? More hints, strange connections? Or will we twist in knots, our minds unable to grasp concepts beyond our reach? There's only one way to find out. If you enjoyed this journey through the cosmos, show your support by liking this video and subscribing to the channel. Share your thoughts in the comments below. We'd love to hear what you think. Thanks for watching, and we'll see you next time. Why disagree? Despite holographic theory's allure, nothing has been proven after decades. We haven't cracked string theory or proven ADS/CFT. Black holes remain mysterious. String theory is on shaky ground after the Large Hadron Collider found no evidence for supersymmetry, a key component. Without string theory, the holographic program may be at risk. Perhaps steam engines are just steam engines, and black holes only coincidentally resemble them. Maybe we misunderstand entropy and quantum information. Perhaps we've been wrong all along. Is this a warning? Is the universe telling us something? What will we find if we keep exploring? More hints, strange connections? Or will we twist in knots, our minds unable to grasp concepts beyond our reach? There's only one way to find out. If you enjoyed this journey through the cosmos, show your support by liking this video and subscribing to the channel. Share your thoughts in the comments below. We'd love to hear what you think. Thanks for watching, and we'll see you next time.